It's our pleasure to have Ekaterina Fokina at the Midwest Computability Seminar. And today she's going to tell us about algorithmic learning of structures.
Thank you. Thank you for inviting me. Yeah, so let me start with a general motivating setting for all this project. So suppose we have a class of countable structures, like suppose that we are stage by stage seeing one of the structures from this class, larger and larger finite pieces of the structure. And then the question is, can we, after finitely many steps, somehow identify the structure or classify like which of the structure we are seeing up to isomorphism or maybe some other equivalence relation? And well, there are quite some issues that have to be formalized here. But before I do this, let me show you that this is a not trivial question, even in the case where we consider like just isomorphic copies of two structures. Yeah? So our class consists of isomorphic copies of just two pretty simple structures, A and B. Equivalence structures. A has equivalence classes, infinitely many equivalence classes of size 2, and B has infinitely many classes of size 2 and one class of size 3. And so suppose we are seeing one of the structures here, these finite pieces. Can you see my pointer? Can you see this hand? Okay. So here are my finite pieces. So I see, let's say, a class of size 2. No? And well, this is the hypothesis I output. I say I'm seeing a copy of the structure A. Yeah, and as long as I see only classes of size 2, this is what I output. And this is my hypothesis. And then if at some point one of those classes grows into a class of size 3, then okay, I start outputting B. Yeah, and in either case, whether or not I see this class, from some point on, I will for sure stabilize to a correct hypothesis, or from some point on, I will output a correct hypothesis. Okay. And well, another example, again, two structures, very similar, equivalence classes of size 2, infinitely many of those, plus one class, just a singleton, just one point, one element that is not isomorphic to anything else, and B has infinitely many classes of size 2. Yeah, and in this case, the same approach as before doesn't work anymore, no? Right? So suppose we see classes of size 2, and suppose we output the hypothesis A. But if we see those only classes of size 2, then from some point on, we have to change our mind and start outputting B. And then the opponent says, okay, here is the possible class of size just 1. You know? And then from some point on, I have to start outputting A as my hypothesis. And then the opponent says, oh, no, here is the second element, which is equivalent to this one. So it's actually an equivalence class of size 2. Yeah, and then I have to change the hypothesis again, and so on and so forth. So there is no way to stabilize to correct answer. Yeah. Okay, so this is a not a trivial question even in these simple situations. So this is another example, omega and the negative integers, omega star. In this situation, we can identify our structure in the limit, right? So as long as we see an element that appears to the right of all the previous elements, we output the hypothesis omega. If we see an element that appears to the left of all elements, then we start outputting omega star. If something in between appears, then we just wait. And from at some point, we will see the zero, the least or the greatest element, and all other elements will appear, let's say, to the right. And then from this point on, we will output omega as the hypothesis, or, well, omega star if we see all the elements to the left, all the new elements to the left. So this is also a good case. And if we have the naturals and the integers, then we cannot do this for like similarly as before, yeah, because we will jump here and there between our hypotheses and will not converge to whatever, to an answer. Yeah, so and yeah, so this is just to give you some motivation and intuition about what kind of situations can appear here. And now let's formalize all this. So, okay, let's talk about what do we mean by receiving these finite pieces. You know, what kind of information we receive when we see those finite pieces. And well, there are two most obvious approaches, but I will talk about them also later. So the first, motivated by computable structures, we see both the positive and the negative information. So we see finitely many elements, and we know how they are related to each other and how they are not related to each other. So if they are not related, they will never become related. And well, a second possibility is that we only receive the positive information about the structure, motivated by computably enumerable structures. So we see some finite pieces of the universe of the structure, and the information how those elements relate to each other, but not the negative information. So at some later stage, they might become related or maybe not. Okay, so I will mention, I will talk about it a little bit at the end of the talk. And then, well, what do we mean by classifying or identifying the structure? What, by identifying successfully this structure, and this and some other issues need to be formalized. And to do this, we use the ideas from, well, computable structure theory on one side and computational or algorithmic learning theory or inductive inference on the other side. Okay, so the computational learning theory is a large field which developed starting from the paper by Gold in 1967. But mostly it concerns either learning of functions or languages. Yeah, so basically unstructured information. So elements are not really related to each other. And well, what we do is applying these ideas, but to algebraic structures. And this is also an approach that was studied also before us, but not very, very extensively. So this is basically a paper that I know about, starting with a paper by Gleimer in '85, and the result later generalized and reworked, extended in a book by Martin and Oscherson. And then a series of papers by Frank Stefan and co-authors. And this goes in a slightly different direction. These papers, they're basically learning some substructures of a large structure, like learning subspaces of V infinity or things like this. Yeah, and what we do is more in the direction of this paper, these results. So we want just some arbitrary classes of structures, and we want to study learnability of this some general classes of structures, not necessarily substructures of some fixed structure. Okay, and to learn those isomorphism types, yeah, so we need to be able to name them somehow. So here we focus mostly on learning of copies of computable or computably enumerable structures, or in general some kind of structures that can be named in a nice way, can be enumerated, that can get natural numbers as their names. Now, on the other hand, we want this learning to be, the process of learning to be independent on the way in which the data appears and in which it is given to us. So this learning procedure should actually work for all isomorphic copies of a given structure. Yeah? So all our classes are closed under isomorphism, and so everything should work for arbitrary, not necessarily computable OCE presentations, isomorphic copies of those structures. Okay, so now let's move to the definitions, and well, I will do it on an example, on an example of graphs, but these are basically can easily be formalized and generalized for an arbitrary for arbitrary structures. It's just easier for the intuition, I think, and to make it not too formal and confusing. Okay, so suppose we have a family of graphs, infinite family of graphs, and each graph just contains infinitely many, let's say graph GI contains infinitely many I+1 cycles. So this is a class that is easily learnable. You know? So we just wait for a cycle to appear, and then, well, we know which of the structure we are seeing. Okay, so we just count how many vertices we have there, and then we output the corresponding hypothesis. And well, let's now introduce all those learning theoretic notions that we need to specify when we define some kind of learning. So, well, the learning domain is the family of all isomorphic presentations of graphs. So, as I said, we want this to work for an arbitrary isomorphic copy of the structures that we have. And then as the information source, so the kind of information that we receive is both the positive and the negative, as I said. So, and this is called learning from informant. Yeah, informant is just basically the set of pairs. So for the case of graphs, so we receive two vertices and the information if there is an edge between them or not. Yeah, and if there is an edge, it will stay forever. If there is no edge, then there will be no edge forever. Okay. So, and then the set of hypotheses is just natural numbers plus the question mark. Question mark is just for waiting before we output hypothesis. We may wait. Okay, the learner in general is just a function. Yeah? So in general, we do not say that it has to be a computable function or anything. So we do not talk about the complexity of the learner in general, but we might if we want to. Yeah, so we might also measure the complexity of this function that learns the up to isomorphism or whatever equivalence relation we want, the structures in our class. Okay, and well, we know that what we are receiving is, those are actually structures from the class. So these are graphs of this form. So this is our prior knowledge. Okay, and the final step. So now we need to say what it really means to learn, to learn this class. It means that whatever structure we are given, finite pieces of whatever structure we are seeing, from some point on, we have to start outputting one and the same hypothesis, and it should be the correct hypothesis for this graph. Okay, so they shouldn't be G1 and G2, they should be all of those GIs. Any of those GIs. Okay, so the only problem here is how exactly we define those hypotheses here. How do we interpret those hypotheses? And so the first and the obvious idea is to say, okay, when we output the hypothesis, let's say M, it means that we are isomorphic to the graph G M plus 1 in these notations from this slide. Yeah, so that basically GI means, the hypothesis M means that we are seeing a graph with, let's say, M consisting of M plus 2 cycles. So in this situation, it is probably a natural and nice approach. The problem is that, those enumerations of classes that we want to study are not always that nice. Yeah. So the general framework here, the general approach based on this idea would be to fix a Friedberg numbering of the class and interpret the output hypothesis with respect to this Friedberg numbering. Now the problem is that Friedberg numberings are sometimes computationally very hard. And so we might use this approach if we want to sweep under the rug this complexity of the enumeration, and we do not want to deal with it. So it, in some situations, it's a nice approach, and there will be results that I show you later that use this approach, and you see that actually the formulation of those results is nicer, okay, than using the second approach. But the second approach was, on the other hand, more precise, maybe from the computability point of view. So we fix a uniformly computable sequence of all computable undirected graphs. And then the conjecture M that we output means that our graph that we are seeing is isomorphic to the graph with the index M in this enumeration of all computable undirected graphs. Okay. And in general, if we do not talk about graphs, but about arbitrary classes of structures, arbitrary structures, it means that we fix some arbitrary superclass of our class that is uniformly enumerable. And then the hypothesis E means that we interpret we interpret this conjecture with respect to this enumeration of this superclass. Okay, and in this situation we get this one more direction, one more parameter in our learning up to which enumeration we are studying. We are learning our classes. Okay, so nu will be the enumeration up to of some superclass, and we interpret the hypothesis with respect to this enumeration nu. Okay, and then, formally, we say that our class is learnable if we have a learner, we have a function that receives these finite pieces of information, positive, both positive and negative, for some structure, and from some point on starts outputting a correct hypothesis as interpreted by this enumeration. Yeah, so the structure with the index E in the enumeration is isomorphic to our structure A. So all these prefix, it completely describes all these parameters that I said. So inf means learning from informant, so meaning that we receive both the positive and the negative information. X stands for explanatory learning, meaning that from some point on, we really need to start outputting one and the same hypothesis to learn the class successfully. Here, another option would be, for example, BC learnability, when we are allowed to output possibly different indices. Sorry. But all of them should correspond to the correct structure. Yeah, so this isomorphism here stands for this isomorphism. So we learn really up to isomorphism our structures. So our hypothesis should really up to isomorphism describe this describe the structure that we are seeing. And nu is the enumeration. Okay, so these are the formal definitions. Is it all clear till now? Okay, so let's then move to the results. And together with Nikolai Bajenov and Lucas Amaro, we were able to characterize learnable families of structures using this notion of learning. And this characterization uses infinitary formulas. So I remind the definitions here just in case. But really, we only need those infinitary formulas for very low levels, only for alpha less than or equal to 2. Yeah? And well, we also, when we measure the complexity of the learner, then we do it using computable infinitary formulas. Okay. C conjunctions of C conjunctions and disjunctions here. Okay, and well, the main result looks like this. Suppose we have a class, a superclass K0, which has a nice enumeration. And suppose we have a subclass K of this superclass K0. It might be finite or infinite, but we assume that all the structures here are pairwise non-isomorphic. And well, then this class K is learnable using all this, using the definition from the previous slide, from 2 slides before. Yeah. If and only if we have a sequence of infinitary sigma 2 sentences that describe structures inside of this class. Yeah? So the sentence Psi is true in the structure Vj if and only if I is equal to j. Okay. Okay, so the statement itself is not new. Appears in the book of Martin and Noscherson using different terminology, but the idea is pretty much the same. What is different in what we do, our proof is completely different and based on the pullback theorem by Knight, Sarah, Quinn, and Vandenboom. And this proof allows us to measure the complexity of the learners. Yeah? And this is what is really interesting from the point of view of computability. So here is this corollary, and this is our new contribution to this. Yeah, so suppose we have an oracle X such that, so we have an oracle and a superclass with a nice effective enumeration. And then suppose we have a subclass K as before inside the superclass K0. And suppose that this subclass K is uniformly described. So structures inside of this class are described by X-computable sigma 2 sentences. Yeah? So there is this uniformly X-computable sequence of sigma 2 computable sentences with respect to the oracle X again that identify those structures inside this class. And suppose also that we have an X-computable way to find indices of those structures that are isomorphic to Bi inside of this general enumeration nu of the superclass K0. Then the class K is learnable by an X-computable learner. So basically, for this X-computability, we need this class to be described by uniformly X-computable sequence of X-computable infinitary sigma 2 sentences. And if the class is infinite, then we need to have a nice way of finding indices for those structures in the enumeration of the superclass. Okay. And now, as the corollary, we apply these results, and we can get learnable classes in such natural classes, among such natural structures: lattices, abelian groups, linear orders, if we have finitely many isomorphism types in the class. But we have no learnable classes for Boolean algebras or infinite learnable classes for linear orders. Okay, and for all those classes, for learnable classes, we can also easily estimate the complexity of the learner. So basically, we can do it pretty much in a computable way. For the examples that we have. Okay, so before I go to other notions of learning, let me just mention here a nice result that that characterizes this kind of learnability from another point of view. It connects this inf X learnability to descriptive set theory. And so this is a new result by Bajenov, Cipriani, and Sanmauro. And they prove that a family of structures is learnable in this setting that I described. if and only if there exists a continuous function that pretty much reduces the isomorphism relation on structures, on isomorphic presentations of structures from K to the relation E0 of eventual equality. And then after they observed this result, they introduced a new notion of learning. One can say, okay, a family of structures is E learnable, where E is some equivalence relation. If there exists a continuous function that reduces isomorphism relation on the isomorphic copies of structures from K to this relation E. And then one might study how those notions of learning differ for maybe different benchmark relations from descriptive set theory. So I will not really go into these details of these results. But they, what they did, they proved that some of those notions coincide for some relation, while for other relations they are different. And they also gave a syntactic characterization of this E3 learnability. What is nice about this notion is that now we can basically define and study learnability for uncountable classes of structures. So everything that I talked about, these were classes with only finitely or countably many isomorphism types in the class. So now one could also do this for possibly classes with uncountably many isomorphism types in them. You just use this general use this equivalence here as the definition. Okay. Learnability. Okay, so what can we? What else can we do here? So there are a lot of open questions here, actually, and one question, or maybe even several questions, can be motivated even from by the previous slide. And now let me show you what other kinds of questions one can consider. Okay, the first, and we can talk about different sources of information. Yeah? So we can talk not about computability, not about learnability from informant, but from text, meaning from the positive information, or maybe even from some more from other levels, maybe in Yershov hierarchy. Why not? So we can go into this direction and aim for syntactic characterizations or just examples and things like this in this direction. The second parameter that we can change here is the relation up to which we study those this learnability. And so maybe we can say that, okay, we study not, so the hypothesis that we output doesn't have to exactly correspond to exactly the isomorphism type of the structure, but maybe it might be something similar, just the hypothesis that we output corresponds to some structure that is somehow similar to the structure that we are actually seeing. Yeah? So we might think, okay, we relax this a bit and we study learnability up to biomodability. Or we may say, okay, we want this index to correspond exactly to this structure. So we study learnability up to computable isomorphism. Yeah? So this is the other way around. Okay, I'm sorry. I have to have a break for for a minute and I will be back. Sorry for that.
It's okay. We'll wait. You could
pause the recording.
Yes. Yeah. Yeah, so meaning learning from informant means that when we receive these finite pieces of structure, yeah, so we receive the finite part of the universe, some finite subset, and also the information how the elements are related to each other and how they are not related to each other. Yeah, so we also get this negative information. And this negative information will not change to positive. So if elements, let's say, think about graphs. If when element appears, an element appears, it is not related to the previous elements, it will never become related. There will never be an edge with previous elements. Okay. And learning from text means that we only get the positive information. So these finite subsets and how they are related to each other, how elements are related to each other, but not how they're not related. So they might be not related for a long time and then they become related. Okay. Okay, so and about this second parameter, I didn't put this into the slides, but in the paper that our first paper with Lucas Anmaro and Timo Kötzing, this is where we started all this. What we did, we considered all these learning notions up to isomorphism, bioembedability, computable isomorphism, and computable bioembedability for the case of equivalent structures. And well, we showed that they are different. That there exist those natural inclusions, and those inclusions are strict. Okay, and okay, but it was only for equivalent structures, for the very simple case. For more complicated classes, we didn't look at this. We only looked at the case for isomorphism so far. Okay, so the third parameter is changing this X, the convergence behavior, you know, the criterion of success. What do we mean when we say that we successfully learn the class? Yeah? So far we had this syntactic convergence, meaning that we had to converge to one and the same index. We can consider also other notions like BC learning, behaviorally correct learning, meaning that we might output different indices, but all of them should correspond to one and the same. All of them should correspond to structures that lie in the same E class, meaning the E, the relation up to which we learn. Okay. Okay, so this is something that we haven't really touched yet, and I don't really know how exactly to approach this, like difference. So for the case of sets, it is known that the BC learning is different from X learning. Okay, for structures we haven't done this yet. Okay, so the distinguishing between BC learnable classes and X learnable classes, so we do not know this yet. And so yet another dimension, what we can consider while talking about learnable or not learnable classes is to consider the complexity of the learner. So to consider classes that are learnable by, let's say, zero jump, but not by, but not computably or things like this. Yeah, or whatever one prefers here. Okay, good. Okay, so let me just mention quickly this work in progress that we are doing for the text. for learnability for this text learning, text X learning. So everything here is the same in this paradigm, except for learning from text. They are learning only from the positive information, and we only get the positive data. But we still have the X convergence, meaning that we want to output one and the same conjecture from some point on. So this is the text X learnability, also up to isomorphism. And this is these are the results where I wanted to show you how they look like when we do not talk about the complexity of the enumeration. Yeah, when we do not look at some classes, what we just say, okay, the enumeration is our hypotheses are basically just the indices of the structures as they're given here. Yeah. Okay. So we do not consider the complexity of this, how this class can be found inside of some superclass with a nice enumeration. And then we could also, with Nikolai Bajenov and Dino Rossega and Alexandra Soskova, Maria Soskova, and Stefan Vatev, we could give a syntactic characterization for this kind of learning using the notion of positive infinitary formulas as given by Soskov. So I will not talk much about those definitions, but okay, these are also some formulas, infinitary formulas. And then we can say pretty much an analogous result. Yeah.
Is the difference just that you only allow positive atomic formulas?
Yeah, so you have also here
no negations.
Yes, so negations you only have negations you only have here. Yeah, here you have negations of atomic formulas only here.
Okay. Okay, thank you.
Mm-hmm. Okay, so yeah, and these are the formulas that characterize text X learnability. So learnability only from the positive information. Again, sigma 2 positive sentences are enough, and this is exactly what we need. And then also, again, we can measure the complexity of the learner in exactly the same way as in the previous case. So if we have an oracle X, and suppose we have a uniformly X computable sequence of those positive sigma 2 X computable sentences, such that those sentences describe structures inside this class, then the family is learnable by an X computable learner. Okay, so yeah, the question here also, well, supposing that BC learnability is different from X learnability, maybe describe those classes, or maybe find syntactic characterizations also if we get the information in some other more complicated way also. Can we do something here? Okay, so I'm done here. This is the list of references to everything that I mentioned, and yeah, thank you.
Well, I would not be surprised if there were some questions. Does anyone want to ask a question now?
Nice talk.
It was very
Do you have
nice
some
talk.
examples of things that were in the last slide, the other structures?
Yeah, not yet. So as I said, this is work in progress. So this is something that we are working on. So hopefully we'll have something now.
So you have a conjecture of what kind of structures would be text EX learnable that weren't learnable before? Or that are, or I mean, either way?
Well, let's see. I'm pretty sure, for sure, you can find these text X learnable equivalence relations. This I'm pretty sure you can do, and maybe we even did this. Maybe not in the paper, but in some drafts of the paper.
I have a quick question, Katja. Do you have an example of characterization with bioembeddability? I mean, like a syntactic characterization?
No. Yeah, syntactic characterization of bioembeddability in general. So, all my experience with bioembeddability shows that from syntactic point of view, it's not.
Right. Well, it's hard to manage.
Not
right.
obvious.
I was just wondering. Right. I was wondering, like, for special cases like linear orders or something, do you have any criteria there?
No. Well, not yet. So this is basically pretty much everything that we know.
All right.
Yeah.
Cool.
So there are a lot of open questions there.
Are there more questions? If not, let's thank the speaker again.
Thank you.
Thanks, Katja.